Hello and welcome back to another episode of Math with Son. Today we're going to be doing AP Physics 1 and we're doing conservation of energy. So the law of conservation of energy, it has a few different formulas, but it's a really simple idea. So rather than writing the formulas and wasting your time, I'm going to point to it and talk. If you take your total mechanical energy, which is your kinetic energy and your potential energy, and you put them together, then it will be your total mechanical energy. And what you start with must be what you end with. Okay, so your total mechanical energy going in must be equal to the total kinetic energy and mechanical energy going out. So K initial, kinetic energy going in, and your potential going in must be equal to K final plus U final. Okay, that is when it is conserved and there's no dissipative forces, which is considered non-conservational forces. And if there are some non-conservational forces like friction, then when you take your initial for your potential and your kinetic, if you combine that with the negative friction of some kind, because friction is always going to be acting against the actual work done, then you will get your kinetical energy final and your U final put together. Okay, so remember that K initial and U initial, those are typically referring to two specific formulas. Your kinetic energy is 1/2 mv squared. So your initial would be considered 1/2 mvi squared. And your potential is almost always mgh. Okay? And your K final would be 1/2 mvf squared. And this would be mgh final. So you take your initials and you take your finals and you use those subscripts. Now the work done by friction is typically going to be the kinetic coefficient times its mass times g times distance. All right, so that one gets thrown in later. And your W of the work of the non-conservation would be the change in your kinetic and your change in potential, which makes sense because however much this changed in that negative direction, whether it changed and was now negative in kinetic or negative loss in potential, that would equate for why you're missing some in the final answer. Okay? So I got one example for you right now, and then we'll get to start to see how this all kind of works together. So we got a roller coaster here. Roller coaster. All right, this roller coaster has a mass of 250 grams, although that won't really matter. It has negligible speed at the top. That means it is starting with 0 speed as it careens and starts to trickle down this ramp. We're going to assume that friction is not a part of this. All right, so with that in mind, we are going to do this potentially two different ways. You could do this all with kinematics, okay? And we'll either do that in the video at the end or we're going to do it in the next video. We'll see. There's a lot of examples for this. Because we just said the word kinematics, you already know this is going to be potentially a long unit. All right, so what is the K initial plus U initial? That would have to equal K final plus U final. So what is the K initial? Well, that would be 1/2 mvi squared, and then mgh for your potential energy will have to equal K final. So the K final would be 1/2 mvf squared plus U final, which would be mgh again, but it would be a height of the initial versus height of the final, assuming it is moved down. We want to find the height at points B and point C. Okay, so remember how I said it didn't really matter what the mass of this thing was? It's 250. Well, what do you notice here? M, 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 and M. They all have an M. You can divide that away. All right, with that in mind, we are also told that the speed at the top of the hill, point A, the initial height, is 0. So if we plugged in 0 here, VI equaling 0 would cancel this entire term out, which tells us that GHI will be equal to 1/2 VF squared plus G times H of final. Now we are looking for the final speed at points B and point C. So let's solve for the final speed. We would subtract the GHF over. So if we subtract it, we get GHI minus GHF will equal 1/2 VF squared. Multiply by 2, and then square root. So if we multiplied this whole thing by 2, we could actually factor out a G and an H, but or G, not a G and an H, minus GHF, and then we would have to square root. Okay, that would give us our final velocity formula. Now, that would only work if we're starting at point A. Okay, this is not a formula for like every formula ever. I'm just kind of practicing what AP does a lot, which is manipulating formulas without actually plugging in any numbers. All right, if we actually want to find this out, we could plug in 10 and we could plug in 25, assuming we're starting at A. If you wanted to, you could start at A, figure out what your velocity is at B, and then use the velocity of B to figure out the velocity of C. I think it'd be easier to just start at A in this case. I did both, and it was definitely easier to figure it out from A. So what is the initial height? 30. Okay, so that would be 2 times 30, I forgot my G, times 10. G is 10. 30 is the initial height. And then this is kind of like a bracket around this stuff. Minus G times H final. Well, G is still 10. Times H final, we're going to plug in 10 for point B. And then we could do the math here, and we could square root it and get our answer, which is 20 meters per second. That would be point B. 20 meters per second for point B. Well, the only difference between point B and point C is that instead of plugging in 10 for your final height, you would plug in 25 for your final height. And if you do that, if you replace this 10 with a 25, you would end up that point C has a time of 10 meters per second. Okay? So, just to prove that this could be done with kinematics, looking back at our kinematic equation, there's a kinematic equation for AP physics that says Vx squared would equal Vxo squared plus 2ax times delta x. Okay? It's actually x minus x sub 0 on the formula sheet. Now, if you recognize that the initial velocity was 0 at the starting point, that would have Vx squared, your final velocity squared would equal 0 plus 2 times gravity times the change in height. Well, if we went from 30 to, let's say, 10, how much did we went down by 20, so that would be a change in height of 20. And lo and behold, if you solve this equation, you get Vx squared is equal to 20 times 20, which is 400, and when you square root 400, you get 20 meters per second. It can still be done with kinematics. It's just sometimes it's easier to use the conservation of mechanical energy. Now, that matters in other problems because kinematics don't really deal with forces as much, whereas energy does. Okay, so kinematics kind of fail whenever you start incorporating friction and other aspects. Okay, kinematics are great, but they don't do everything. So that's why we have the conservation of mechanical energy, and it helps us for figuring those out. Stuttering at the end. I'll see you in the next one when we do a ton of examples. So there's a ton of examples for these. I'll quit rambling. Bye.